So let me give you this information again. So today we start with PDA, and I just explained that PDA is a new construct which has a notion of input tape, which was missing before in all previous mathematical models. This input tape is by nature in size, it is infinite, and it starts from left side to the right side in this direction, and we always write our word cell by cell, letter by letter in this tape, and where your word finish, so it has this symbol of delta, which is a blank sign. It is not lambda, it is not equal to lambda. This is different. Lambda is different. A lambda is a word without any letter. So this sign is the empty word sign, and it's the size of your input tape is whatever the storage size. Here now, when we talk about FA, we can convert our FA into PDA, and PDA has a lot of other constructs. We only choose those constructs which suits to FA. FA is limited. It's not like TG or some other mathematical models. So it will use few constructs of PDA. And now if you see that we have this start construct, accept, reject, and so start is the start state of FA, accept is the final state of FA, and reject is the non-final states of FA. And whenever you have a state, you can simulate that by using the read construct. So when you have a state, so you have two outgoing edges or might be the lambda. So same thing is here. So you have A, B, or lambda as an outgoing edges. And now we have this machine here. We will see how we convert this FA into PDA. You have two states, so you have two read states, and then final state has a this construct, which is for the fixed construct for the accept state, and the start state has this construct for the start state. It is a non-final state. It has a reject state construct, and all other edges are exactly you map the way these two states are connected with the edges and the label. This is very easy, so you can construct your FA into PDA, and you need to understand what are the equivalent construct in PDA available for FA. And now we will see another example here. This is exactly the same thing what we did before. You have three states, so we have three read state here, and you have start state. So we have this start construct here, always connect to the read state, and then we have this final construct here. So we have this accept state, and the two states are non-final states. So you have two reject states. Always this is a fixed thing. The label will be always, in every case it will be lambda. It is missing here, it should be also lambda. And then you just connect accordingly. So it has this A to the next state. We have A here, B go back, so B goes back, B is self, so B is self here. A goes to the next, A goes to the next. A and B is a self, A and B is a self, and you can draw your FA into PDA. It's very simple. So you just need to understand what are the equivalent construct of FA, a PDA, and then you can draw your FA into PDA. And now this is a new thing here, new data structure, which is array data structure you have, oh sorry, this is stack data structure you have. And you can have a notion when you talk about stack. We know that stack, how the stack work, it operate with two operations, push operation and pop operation. So now initially when you have a stack in your PDA, stack is also empty, and when you have empty stack, all of its memory locations will be delta, so means there is nothing here. And as soon as you push any information into the stack, so it will write that location and replace that delta with whatever you want to push into that. And you know that the process of stack is first in, last out, or last in, first out. Whatever the value you enter first, it will come out at last, and whatever the value you enter last, it will pop out first. So push is used to store the value into the stack, and the pop operation is used to pull the value from the stack. So you perform push operation here, and you have B here, and when you perform pop, so whatever you push in last, it will come out first, and the next value will be at the first position. So this is a standard procedure of stack, and we can use this data structure in PDA also. But this data structure does not use when you use FA. It is for some other mathematical models. Okay. So now look at this one. For the stack, how we perform this operation, what are the constructs we use in our PDA. For push, we have this kind of construct. For pop, we have this kind of construct. So pop is quite close to the read, but the sign is exact something like that, the diamond sign, but it has pop here. So you can pop as many values you want. But it behave letter by letter here. So you can always pop or push one letter, because the storage capacity of each cell here is to store one letter. Okay, so this is the way we can deal with this. Let's see one example here, and then you can get better understanding of this. So this is one machine here, and if you see, it has a word A, and we know that this is non-regular language because it is ANBN. And you know that when you have any non-regular languages, you cannot write regular expression for that, or you cannot draw any FA or TG for that. But look at this, we have this, but we have this PDA push down automata that works very fine with this machine. So now when you have this machine, someone already created this machine for you, and we have our input tape here, which has our word written there, A. Look at this one. This is your input tape, and you have this word written here, A, B, and then where your word finish, you have delta there. So now here you want to see that, and you want to pass this word to this machine, and want to see that whether when you finish this last B, which at which construct you are. Are you at the accept state, or you are at the reject? If you are at somewhere reject, it means this word does not belong to this machine or this language. If you are at the accept, it means this word belong to this machine, and this is a valid word. This is what we will do. But this machine will be given to you, and the input tape will be given to you. So what I expect you learn in this, just how we do the dry run on this machine, if these both things are given to you. How to draw FA, PDA for non-regular languages. It is quite hard. I don't. It is not in your scope. But to draw the PDA for regular languages, that is in your scope in this course. Okay. So now we will try to dry run this. So look at this. So we start from this machine, from this state, and we come here. And here we encounter read. Read says, read, when you encounter read, read will take you to the input tape, and your initially your index is here, and you start reading from the input tape, because always you start reading from left to right, and automatically once you read one cell, automatically machine will do the increment of your index position, and it moves to the next cell. So when you perform read operation here, it could transfer control to the input tape, and you read A here. So it says what you read. You read A, B, or delta. So we read A there. So we are saying, okay, if you read A, perform this job. What is this job? Push A into the stack. So let's see, go to the next page. So I push A into the stack. The value which I read, I cut that from the input tape, and now my control goes back to here. I am here again. So I go here again and says read. So now if you see, after this, my pointer should move here. and I cut this because I already read this. It says read again. What I do, I read again here. So until you have A here, it will do the same job. Read A, push A, read A, push A. And what happened? You reach to this state and you have your stack will have three A's there. So look at this one. So you read, cut three times your A and your stack will be three A's there and your control goes to this at this point. And now once you are here, you again come back. This will take you to here. Your location is here and you read again here. So once you read now, you read B. It says if you read B, then what to do? It says if you read B, then come here. What is this? Pop. Take out the last value which you push into the stack from the stack. So what was the last value? Last value was A. You enter this A there. So we take this out from the stack and the stack will have only two A's. Look at this one. We take out the value of stack and it has only two A's now because we perform the pop operation. Once you do that, let's see what machine says. It says if you pop, what you pop from the stack? I got A from the stack. Okay, you got A from the stack, then move on this side. What is this? Read. I read B here. Okay, if you read B, go here, perform the pop operation. And I know that I have two other A's there. I will pop another A. You pop another A, come here, read. And then I read what? I read B here. Okay, read B, go here again, pop. I pop A from the stack. A, come here, read. Now what I'm reading? I am here and I read delta. When I read delta, it says if it is delta, go here. What is this? Come here. So now pop. What I pop from the stack? Stack is empty. It has only three A's and now it also has delta. So I have delta. I come here and I finish at the accept state. So now my word will be accepted. So to the word should be accepted, it must you need to check that you should your pointer here should also be at the delta and your stack should also be empty. Look at this one. So your stack is, we read all three B's and the stack is empty. So if you reach at the accept state in your PDA, so then you need to check that two things. Your input tape should be empty, means all things should be gone. You should be here and your stack should be empty. Okay, and your stack should also be delta. So look at this one, our stack is also delta. So once you have both delta there, it means that you are good and your word should be accepted by that PDA. This is a valid word. It belongs to that language for which you design your PDA. So my only expectation is you should know how to do the dry run for this. So all this, what I just explained to you, I write here for your reference. All regular languages can be accepted by some PDA because they can be accepted by some FA, and FA is exactly like PDA. FA never use stack. FA never use push operation in the PDA. FA never use pop construct in the PDA. FA never use stack in the PDA. FA only use accept, reject, read, that's it. Or so these are the only constructs. So and you saw that we successfully draw PDA for the non-regular language, and this is written here that AN/BN, which we just saw, is a non-regular language, and it is not possible to draw FA of that. But look at the power of this machine, that this machine is taking care of non-regular languages and very easy way. So this is PDA is very strong. It takes care of regular and non-regular languages. Okay. So now that's your PDA. So now we will see more examples here. when PDA dealing with regular languages, it is um, it is deterministic. But we will see very soon that PDA sometimes behave non-deterministic way also. Okay, we will see that. So now we have this PDA. It says that this is a palindrome. Palindrome means that you can read from the right side or you can read from the left side. It can be read in the same way. So now we have a word. So this is our partial design of PDA. So we start from here, we read, and read A, push A, read B, push B in the stack, and then you have this read X. Once you read all those A and B here, and when you read at X, so you move to this side, and then there is another design here which is on the next slide. So you read all those operations, and once you reach at X, so then you have this design, and so then it comes here, and it is simple dry run. Huh? So you read, you come here, it says read. So you need to go to the input tape and read what is the value there. If it is B, so then pop. So what it is doing, so then if you pop from the, so it will do the read and pop operation. First it will put all the values in the stack, and then it will pop same number of times, perform the read operation and delete the value from the stack. And once everything will be done, it should check that whether your stack and input tape both are empty. If both are empty, it means this word is valid for this machine. If it is not, it is not valid. So that's what it is doing. Okay, so we just do the simple dry run here. I mean, we are not doing any sophisticated job here. Any question here, guys? Good. Okay. So now PDA without reject input string crash when it has no path to follow. You can use PDA to draw NFA. So NFA, you know, that does not take care of garbage collection. NFA, a non-deterministic finite automata, it can crash. So this is example of that. So now if you see this, you do not have this reject state, you only have this accept state. So it means that when you encounter something which is not handled by FA, by this machine, so it will crash. Okay, so now this is again, if you see this, you have this word A, B, B, X, B, B, A. You wanna go here, you said, okay, start and read, and you read from the input tape, and you read A, push into the stack. Okay, we have stack, so push into the stack A, come back, read again, you read B, push into the stack, come back here, read again, you read B, push into the stack. You did this, and now you read X, go here and perform again the read operation. So you read B, so you come here, pop from the stack. You take out this from the stack. So what you pop? I pop B. Okay, come here. Again, read from the stack, from the input tape. I read this B, read B, come here again, pop from the stack. I pop this also. And I pop B, I come here and I come here. So now again read. I read A. This is A. I read from, so read from the, sorry, this will be here. I read here. I read from the input tape. I read this A, and A will come here. So pop from the stack. What is A? Stay in the stack A. I pop it, and now after popping this, I have nothing left there. So A and come here. And then it says read again. So here in the input tape is nothing, because after that delta. So I read delta. I come here. Pop again. I pop, it is delta. I this and this finish here in the accept state. So this is the way, so you can draw this. And when your FPDA is deterministic, it is easy to do that dry run, because you do not, it does not require human wisdom that or any decision which you need to make there. You are simply following the instructions, and you are simply doing the dry run. But when your PDA is non-deterministic, then it is impossible sometimes for the human being. With the naked eye, you can do the dry run of that, because it requires a lot of human wisdom to make a decision that what to do at that time, how you switch from one circuit to the another circuit. You will see in the coming slides. So this is all, I just draw this here. And now look at this one. This is another palindrome. This is PDA. And this is basically your non-deterministic PDA. Because if you see here, when you start from here and you read here, it says read A. So you read A, you can go here, or you can go here also. So now you have two choices, read B. I read B, I might go here, I might go here. So now here this is non-deterministic PDA. Here it requires human wisdom that at what stage you should switch from this part of the circuit to this part of the circuit based on the given uh, input, and you need to see that what you want to what is the final word you have in your mind that you want to parse on this machine, and you want to see that whether this will be accepted or rejected. So this in this case it looks very hard. You cannot do this by yourself. So we require an algorithm here which can follow and which will help machine to deal something which is non-deterministic by imposing some rules and restrictions in a deterministic way. So now here it is very hard for you. Look at this one, how complicated its table will be. So now if you have this machine here, so you are saying, let me clean this. So perform, let's say we have this word, huh? B A B B A B. So now you read this, and at some stage you decided here now when you read B, you read B. You go to the push B operation. Look at this one, push B. So it means you are going here. And then at some stage, push A, push B. You look at this one, push A, push B. So still at this stage, you are here. But at some stage, you move to you read B and you go to the pop operation. So you decided now I should go to this side and I go here. So this is because you have the target word in front of you and you want to validate that by this machine. So you need to perform this dry run in an intelligent way, that the way you choose the at the different timing your circuit, it should be able to accept the word. So here look at this one. So push A, push B, and that's why I draw this for you, that to show you that it is very hard. Look at this one. So then finally you will be able to accept the word, both stack and both what do you call this, your input tape will be empty and then your word will be accepted. So what I want to emphasize here, that the non-deterministic PDA makes your life not easy. It is hard for us to do this without any so we require any particular algorithm to deal with this, okay, when your PDA is not deterministic. So now look at this one. We have some questions, and we need to find the answer of that. That why it is necessary to define PDA as non-deterministic machine. Why it is important. Uh, why? Because we also saw in previous chapters, when your machine is non-deterministic, so this non-deterministic behavior makes our machine more powerful. We need more strong machine, more powerful machine. But problem is this, that when you have non-deterministic machine, it requires human wisdom there. Human should be jump in and make a decision, and we don't like that part because we want an autonomous machine which does not require human input. So we need to make some rules, some restrictions, some algorithm that we can use on these non-deterministic machine which can behave in a deterministic way. So that's the reason that why we like non-deterministic machine. To construct new machines, make several architectural decisions. Should we include memory device? Yes, we need to include a memory device. So what kind of data structure? Here we will use stack, queue, or random access. We want to use a stack. Can you use more than one stack? No, we will only use one stack. Is this is deterministic? PDA is not deterministic. No. It has finitely many states? Yes, it has. It can has as many states, but it will be finite. Can we write on the input tape? So far, no. We have input tape. We are only able to go and read cell by cell in from left to right direction one by one, and we can only read that. We cannot move back. We cannot write on the input tape. We just able to read that information. Can we write? No. Can we reread? I mean, if you read something here and you forward, can you go back and reread that? No, we are not able to go back and we are not able to reread that. So these are some restrictions so far we see in PDA, and all PDAs respect these restrictions. PDA does not have this ability to use input tape in a dynamic way. Because why we are saying this? Because when we talk about the data structure, stack, queue, or tape looks like kind of array. So we are very mature. We know that how you can move forward or backward in the linked list, how you can add a new value in a linked list, how you add a new node in the linked list, how you edit the existing value of linked list, how you traverse between the linked list or the tree structure. And so we have all that information, yes. So, but in this case, we will not do that. Later we will do, definitely. So now this will tell you the scope of that. If you languages accepted by FA, NFA, and TG all are here, it's a regular language. Language accepted by PDA, and somewhere here you can say that at the same level you have non-regular languages also. Language accepted by PDA is here. PDA will take care of all these languages and this languages. And then here language accepted by non-deterministic PDA. So non-deterministic PDA will take care of this languages, these and these. Okay. So it has a big scope. It takes care of everything which is here also. And this is the formal definition of PDA, which you just see that PDA is a collection of 8 things. So whatever we just saw that we write in a formal definition, PDA must have the input letters, and the input letters come from the summation. Summation is equal to whatever the constructs you have, letters you have, A or B or whatever. Input tape, which is infinite in one direction, initially contains sequences of input letters starting in the first cell. The rest of the tape contains only blanks, that is delta. In the stack, you have different set, which is gamma, which you use to write in the stack. So far, we have the same A or B. We push that into the stack, but it says that for the input tape, the values you will get from summation. For the stack, you have another set, and this can be these values. Okay, so it can be same. It can be same A B A B. It can be different. So you can have, let's say, 1 0 and A B. It can be different. It can be capital letter A or B or numeric values, whatever. Or might be it is same. So far we saw these are same. That's why our value in the stack and our value in the input tape, we don't feel any difference. But we have these two different sets. So at some stage when you feel that you want a different value, so you can have different value there, you will not mess up. So let's say you say I perform this gesture, this is the input value, and this is your robot which can perform some job. I said I perform this gesture, and this gesture I will say, let's say I perform a circle design in the space, and the robot will perform this job, and robot will wake up or start moving. So these are the set of jobs, and these are set of gestures, set of instructions. Okay, so this way, that's why we have the two notion of two sets. One is for the input and the one is for the output. Both can be same. You will say A, robot will say A. You will say B, robot will say B. Or you can say A, robot will say thank you. You will say B, robot will say bye bye. So you can have different value set or the same set. But technically we have two different sets which have the values there. It can be same, it can be different. A PDA has push concept of stack, which we will not use in FA. When you convert FA into PDA, this is only for non-regular languages. The stack is initially empty. We have the start state notion, we have a set state notion, we have a reject state notion, and then we have this push X, we have read, we have pop. We saw all these operations, and we know that when you have input tape initially is empty. When you have a stack initially is empty. And what it has this delta. Okay, it is not equal to lambda. Lambda is different thing. Lambda is not the delta. So now you have so now we have more examples. We have this grammar here, and we want to see that how we design this. We have this context-free grammar, and we have this given PDA, and we want to see that whether this is a valid word accepted by this machine or not. So now you have this start push one s. You always start from here. You have so many push operation here, so you assign that with values 1, 2, 3, so you will not forget that what operation you are talking. So you start from here, push one, and then you go here to pop, and then so you see this is non-deterministic PDA. So when you perform pop operation here, might be you get S. If you get S, so you have multiple ways to go by S, this way, or this way. So this is non-deterministic. So you should know that what kind of that input you have, and you want to see that option, you want to choose that option which suits you and leads you to the successful acceptance of this sentence. So this is not deterministic, and it's very hard. It requires a lot of experience to figure out that at what stage we should switch from one circuit to the other circuit. Okay, so it requires more experience for that. Look at this one. So how long this table will be, and then you perform all these operations, and then you should be able to figure out that your word will be accepted. I will not ask you these kind of non-deterministic PDA in exam to do the dry run, because does not make sense. But we have this thing here to give you idea that if you have something like this, so how hard it is. Uh, and then we will handle this by another mathematical model, and we will see that how we handle that. So every regular language L, there is some PDA that accepts it. So now we are saying that there is an FA that accepts language L because it is regular. We transform this FA into PDA using the constructive algorithm. We already see that. So difference between PDA and FA is the length of the path. So FA will have a limited length. PDA, you can increase or decrease its length. So we can see one example here. So we have this regular expression, and then you are saying that I want to design PDA for that. So for this regular expression, what this regular expression, it says if you have A here, your word will be accepted. We don't care what's going on after that. You may have, you may not have. So the simple PDA for that, you start and read A and the word should be accepted. That's it. You don't care what's going on after that, and you don't need to even draw that, because you just draw what is necessary for this one, and it is mandatory. The A should be there and it will be accepted. So just three states, and we did this. Look at this one. We have just B here to be accepted. So one easy way is start, read, if it is B, easy way. Or you can here start, read, B, and then again read. And you know that when you perform read here, it is input tape, it has delta, delta, delta after that. Read delta, read delta, read delta, read delta, and then accept. So you can use, I don't know how, so here you are basically uses the resources to do the same job, which is possible by using the less resources. But just to show you that this is possible in your PDA, that you can have more number of states to reach to the final state. This is a difference between FA and PDA here. It's good. And then look at this one. So an infinite path. It is also a possibility that if you do not have ability or command on the design of your PDA, you might end up with the infinite loop. Look at this one. So you are saying that, so this is at all words that start with an A and loops for every on any input starting with B. So let's say you have a word A and B. So this is our input A. Okay. So we start from here. It says read. We read A. It says read A, accept. Just accept the word. So word will be accepted. But if you have a word which is uh, which starts with B, something like this. So it says read, and we read B. Okay, if you B, push A into the stack. We push this, pop. What you pop? You pop A from the stack, and now it is delta. We pop A from the stack. Come here, and it is not on the read, it is after the read. So what it will do, it will come here, it will push A into the stack again, push A into the stack and pop, take it out, come here, push A. So this will be a loop here. So it will push into the stack and then pop, push into the stack and then pop, and you are in the infinite loop here. You will never come out from this loop. So it's a wrong design, it's a weak design. So this will be not good. You need to be careful when you design something like this, that it should not have any infinite path in its design. Okay, so this is one thing. And now we are saying that the criteria of your word to be accepted by PDA is that your stack should be empty, your input tape should be empty, and then you finish at the accept state, and then word is a valid word, and it should be accepted by your PDA. This is a criteria. So if this is a criteria, why not we design a circuit which is a fixed design, and it check this thing by itself. We do not need to go to see that whether we reach at the accept state. Now look at this one, our input tape is empty, and then go and check our stack is empty, and then we say, oh yes, we are both are empty. We do not need to check manually. So and then we say, oh okay, we are at accept and it should be accepted. Why not we create a circuit in a way that design itself check that the input tape is empty and the stack is empty, then it should go to the accept. So then we are saying, okay, now we will not just draw accept. Before accept, we will have this thing. Now this will be fixed. It will be before accept. What is that? Once you reach here from somewhere you are coming, read. Read will go to the input tape. If it is delta, then go to the pop. It will go to the stack. If it is delta, then accept. If it has anything, perform these jobs here. If it has anything, perform these jobs here. And make sure that you should have delta there. So this design is now fixed design. Where you use accept here before, now you will use this design always as a fixed circuit, and this will gives you guarantee that whenever you reach at the accept state, your input tape and your stack both will be empty. Okay, that's it. I think that we should stop here. We will start this. We will start the next chapter in next class, and then we can have uh, more stuff to do. So next time I will finish 2 chapters in one class, I believe, because it's less stuff. Any question, guys?